Okay, we're recording. Good. Okay, so before I forget, I'll have office hours this afternoon. They'll be between 1 and 2:30, and I'll send you the link for those. And all we're going to do today is basically qualitative descriptions of Faraday's law. In particular, we're going to concentrate on that dumb little minus sign, which is called Lenz's law, because I wanted you to understand what that means and what we can do with it, and it's going to be quite cool. Okay, so we started with our last one of Maxwell's equations. It's called Faraday's law. And again, Joseph Henry discovered it first, but he did not publish. Faraday came along and got the result, immediately published it, and then it's called Faraday's law. And as far as practicality goes, a lot of the devices we have today make use of Faraday's law. It's actually, from a practical point of view, probably the most important law that we have. I'll try to convince you of, okay, let's say you want to be a spy or something and you want to basically have an electromagnetic pulse weapon to take out a power grid or who knows what. It turns out you're going to use Faraday's law. That's going to be the basis for all electromagnetic pulse weapons and all sorts of things like that. And I'll explain why there are naturally occurring electromagnetic pulse weapons. They're called solar flares. And I'll talk about, hopefully today, a case that occurred in Canada where basically it took out Canada's power grid on the eastern part of Canada. It took out their power grid, a really massive solar flare, and we'll explain that. It's actually easy to understand. So what this is going to state, this all states that a changing magnetic flux. And it's really going to be, in almost all cases, the changing electric field, okay, magnetic field, causes an electric field. Okay, and then what we're going to find out later on is that then a changing electric field causes a magnetic field. That's going to be Maxwell's contribution. And the way this is often worded, it's often worded a slightly different way. You'll say a changing magnetic field or magnetic flux causes an induced current. And so what we'll do today is I just want to talk about descriptions of this, and then we'll have a little dog and pony show on Monday. So what I'll do on Monday is I won't share the Blackboard with this. I'll just, you'll just be looking at me. I rated our prep room for a whole bunch of demonstrations, so I'm going to do a whole bunch of demonstrations, and I'll do that on Monday. I'm a little reluctant to do them since I have to do some board work first. I'm reluctant to kind of switch because sometimes in the switching, funny things happen. And so I think I'll just leave it like this. So, although maybe it won't. So what I want to do today is go back over what we did last time, just really quickly. And then I want to explain what that dumb little minus sign means, that Lenz's law. And that's all I want to deal with today, which isn't hard, but it is a little on the odd side. So what did we do last time? We stated that Faraday's law is, we have that script E. We said this is called your EMF. Okay, this stands for electromotive force. And really, what this is going to be, this is really going to be nothing but a voltage. So this is acts just like a voltage difference. The difference is going to be that the electric field connected with this one is going to be non-conservative. The electric field with what we had before is a conservative case. And what this is going to equal, this is going to be this minus the changing magnetic flux with respect to time. This is your magnetic flux. Okay. And the difference with this is that this is not the magnetic flux through a closed surface. So this is the magnetic flux through a loop, not an imaginary, not a closed surface. If you have a closed surface, this is actually, that's odd. Okay, that's something appeared on my screen. So if you have a closed surface, you know the magnetic flux is actually equal to 0. So for a closed surface, your flux here is 0. And again, the way I described it is, you imagine you have a balloon. So imagine this is a balloon. I'll fold it up like this. Obviously it's not. But imagine this is a balloon. This is a closed surface. If I have some magnetic field going through here, if I calculate the flux through this entire thing, it equals 0. And all that means is that in one part we have the B fields going into it. That'll be a negative flux. On the other part, the B fields, the B lines are coming out of it. So that'll be a positive flux. And those contributions cancel, giving 0. In a case like this magnetic flux is, let's say I have a loop, and let's say this loop is a square. Okay, I have a square loop, and there's some magnetic field coming out through here. That's what this flux is here. It's not a closed surface, even though we're going to write it the same way as for something like this. Okay, the distinction between this one equaling 0 and this one not equaling 0 is confusing, but does that make sense? Okay, yes, okay, good. Now, the way we did this is, obviously I can't prove it at this level. If you want to see the real proof, when we offer our advanced D&M course, take that, and it'll be worked out for you. It's actually quite amazing. It's actually incredibly amazing. We gave a plausibility argument. For Faraday's law. And I want to do this again, even though we did it last time, because I want to tie this into Lenz's law, so I need the same picture. Okay, so what did we do last time? We took our little bar magnet like this, north and south pole, and here was a little loop. Here's some loop. And we took this and we physically moved this down here. So we grabbed this loop and we moved it down like this. And we said when we do this, you're going to end up with an induced current. And we said the induced current is this. It goes that way. So that blue there, this is your induced current. This is the induced current in the loop. And we could say, well, why do we have an induced current? Well, we know. So here's the metal. And so let's say before we moved it, you happen to be a little positive charge here sitting by your lonesome. And let's say you had to be another little charge here sitting by your lonesome. And what would happen to you? Well, you have a velocity this way going like this. This is V. This is V. And we have a magnetic field from this magnet. And this is the north end. So this kind of flares out like this. It flares out like that. So if we're here, we're going to see that magnetic field go like this. If we're over here, we're going to see that magnetic field like that. We applied F equals QV cross B to both of those. So we did the V cross B. That gave us a force going into the board on that little charge. And the force on this little one was coming out. So we said if we're pushing the charges here on this side and pulling the ones out on here, if you do that for the whole loop, that's going to create the induced current. That's what physically was causing it. Just kind of our old result. But then we said, well, let's do a different, let's consider this from a different point of view. Let's say we're an observer moving with that loop. So in a case like that, here's the loop, and we happen to set up our little home there. And here's our bar magnet like this. And from our point of view, we actually see that bar magnet coming up toward us. We don't see anything else. So if you look at that magnetic field, that's like that. Now, what does this person have to see? This person still has to see that induced current. So that no matter what, because that's a real physical thing. So this induced current is still there like that. That's physical. But what would this person be forced to conclude? This person would be forced to conclude is what's causing that induced current? Well, this magnetic field is getting closer. So you're getting closer to this end, so it's increasing. So this person would say, oh, well, what's happening here is that the magnetic field going through that loop is changing with time. And that changing magnetic field has somehow creating a current. And how do I get currents to flow? Well, I know I need a voltage. And how do I get a voltage? I have to have an electric field. So this person would conclude that this induced current is produced by some sort of electric field that exists in this wire. And that's actually produced by basically this changing magnetic field. And if you do a lot of experiments, what this person would find out is that that the voltage connected with this induced, or let's say, they'd find out that this induced current was somehow proportional to basically how that magnetic field was changing with time. They would find out this experimentally, and if you do more experiments empirically, what you end up with is Faraday's law, that the script E equals this guy right here. Okay, that is not a proof. It is not meant to be a proof. It's meant to be a plausibility argument showing you why this is at least possible. Again, if you want to see the real proof for this, take our course in Advanced D&M, which will be offered next spring, and you'll see this in more detail than you can possibly imagine. It's actually a beautiful course. Okay, are there any questions with that? So all I want to do today is talk about basically this equation, and in particular, that little minus sign. That's all we're going to do today. Any questions so far? Okay, I'll take that to mean there isn't. So that minus sign here, this minus sign here is given a name, and we call it Lenz's law. And Lenz's law, again, that's kind of a fake minus sign. It's there, but it's not there. That's a tricky minus sign. That's one of the trickiest minus signs in physics. So what this law is going to state, and just write this down, it's going to make no sense until we do some examples here. Lenz's law is going to give the direction of the induced current. So this gives the direction of the induced current. And what does that mean? In other words, if you look over here, this current, induced current is going this way. Well, you can actually get that from Lenz's law. So I'm going to write down what it is. It's going to be kind of a weird description. We're going to flesh this out. So Lenz's law states that the induced current will be set up in such a way as to oppose the change. And that word change is really, really important, because that change is going to be a lot more complicated than you think. It's a way to oppose the change in the magnetic flux. Going through it. Okay, that's what Lenz's law states. And I'll try to convince you later on that Lenz's law, this is really just going to be it's going to be an odd statement of conservation of energy. If this wasn't true, you would violate energy, but we don't know that yet. So what I want to do is I want to show you how this works. So I want to go back to this whole picture here, and I want to analyze this picture using Lenz's law, show you how that works, and then we're just going to do a whole bunch of examples here of it for the rest of the day. And if I feel brave, I will even try to do one demonstration here in front of you. What I'll do is, before I left, I actually went to the prep room at Alfred, and I took our, okay, it just said my internet stable is unstable. It says my internet is unstable. Hopefully it's gonna be okay. So before I left, I went to the preparatory room of this, between the physics rooms, and I pulled out our electromagnetic weapon that we periodically launch on neighboring cities. And so what I'll do is I will launch this missile basically at Alfred, and then we'll see if we can lose all the internet connection here. That'll basically be our demonstration for the day. Well, it won't be. I have a slightly more mundane demonstration. That's so fun. Not like launching an EMP, which would be cool. Okay, so let's go back and reanalyze this. So let's go back to this picture here. And if you guys have some colored markers, pull out your colored markers. Okay, so let's go back to this case here. And let's do the case where this is moving up like this. Let me make this a little more like that. So when you do these, I can draw in my first magnetic field. So this is here. Okay, so there's some magnetic flux going through here. Remember, your magnetic flux is this double integral of B dot dA. Okay, now, again, so a top view of this, if I were to do a top view, right? This would be your donut. You'd have your dA going like this. You couldn't have your B, it'd be hard to show, but your B would be coming out like this at some angle. And so I would take basically this B here coming out through, right, because this B is coming out at an angle. You have this B here, I dot it here, I'd then some of those, I'd integrate this over this whole region here, and that'd be my magnetic flux. Now, if I'm taking this magnet and moving it closer here, I'm actually increasing this magnetic flux because I'm getting closer to this end here. So I'll say, so we're going to have a lot of words in this stuff today, a lot of sentences to copy. As the bar magnet is moved toward the loop, okay, the magnetic flux going through the loop in the up direction increases. All right. So in other words, there's some magnetic flux coming out of this thing here like that, and as we get closer here, it's increasing in this direction. According to Lenz's law, this loop wants to oppose that change. Now, what is the change? The change is that the magnetic field, the magnetic flux in the upward direction is increasing. So how can it oppose the magnetic field increasing in this direction? This thing has to create an induced current in such a way that it creates a magnetic field going in the opposite direction to oppose that change. So draw that in here. So I'm going to draw this like this. I'm going to put the arrows this way. Okay, so that blue there, this is the blue here. This is the, and that marker doesn't really look happy. So this blue here, this is the induced B field of the loop. Okay, so that loop itself is actually creating its own magnetic field in an opposite direction to oppose that change. So to oppose this increasing flux, I should say magnetic flux, but I'm just going to say flux because it's the only flux we have right now. To oppose this increasing flux, the loop induces a current to create a downward B field opposing this increasing flux. So this blue that I've drawn here, that's your induced magnetic field. Now, what has to be the direction of the induced current in that loop to produce this field? You have to use one of your right-hand rules in reverse. So you tell me, which right-hand rule do we have to use to produce this one? And that gives us the direction of the current. So how do we do this? You have to use one of your right-hand rules in reverse. Fingers in the direction of B. Yes, that's exactly what you do. So you take your right, remember we had the one that said that if the current was going in a certain direction, we wrapped your fingers in the direction the current went, and our thumb points in the direction of B? Remember that one? Well, here, what do we have? We have B. So I point my thumb in that direction, and my fingers wrap in the direction of that induced current. So that induced current has to go like this. That's how we got that. Now, at the B's coming out here, what does this look like? This looks like a North Pole, right? Now, I haven't proved this for you, and I'm going to prove this for you later today. It's something that a lot of people don't do, and I want to show you how it goes. But I think everyone knows this, and so I don't feel bad about doing this first. If you have two North Poles together, so let's say I have two bar magnets, and let's say the caps here are North Poles. If I take two North Poles and put them together, you know that they repel each other. I'll prove that to you later on, actually later today. So these two actually repel each other. So what happens here is that if you were to actually take this bar magnet and move it up like this, you would actually feel resistance in your hand. You would actually know, you could just easily do this. You're actually gonna see you're gonna actually have to physically work to put this in here. That's kind of cool, okay? So that's actually Lenz's law in practice. Now, what I wanna do is I wanna take this magnet and move it down like this. And I wanna show you what's gonna happen in that case. So let's repeat this, but go in the opposite direction. So first of all, are there any questions with that? So this is the same problem now going downward. Okay, so let's draw our magnetic field. So when you do this, you always have to draw magnetic fields and stuff like this. Like that. So here's this. Now what's happening to our flux? So remember our flux is this. It's this B double integral of B dot dA. I'm going to do it for that whole opening here. Well, if I move that magnetic field away from this like this, if I move it down, the magnetic field is getting weaker because basically I'm moving the field here. And so if I weaken this magnetic field, I weaken the flux. So as the bar magnet is lowered, what's going to happen here? The magnetic flux in the upward direction decreases since B is getting weaker because I'm moving the magnet away. So what is the change in flux? Because you always have to ask yourself, what is the change in flux? The change in flux is that the magnetic field going in that direction is getting weaker. So how does this have to oppose it? This has to oppose it by creating a magnetic field going in the same direction to bring that flux back up to what it used to be. So to oppose that change, this one has to create its own field. Again, the blue is going to be our induced field. Like this. So this is the induced field. Okay, so to oppose this change, decreasing flux, okay, the loop creates its own field in the same direction. Okay. To bring the field back up, to bring the flux back up to what it used to be. So we have to ask ourselves, how do we then get the direction of the induced current? Well, we have to use that right-hand rule in reverse again. We point our thumb in the direction of the induced B field, like that. My fingers wrap like this. And so that's going to be an induced current going that way. So this is our direction of the induced current. Now, if the B fields are going in on this side here and out on this side here is acting like a south pole. That's acting like a north pole. Well, what happens if I have a north magnet and a south magnet like that? Well, you know that opposite poles of magnets attract. So if I actually had this and I was physically moving it down, I would actually feel a tug on my hand that would actually be preventing this from moving. That's pretty cool. Okay. Are there any questions with that? Okay, so now you can see something here. What would happen if I took this here, unless I went up, down like this, I went up and down like this? What would happen to the current in this ring? Oh, somebody wants to know why are we using the closed surface integral? Okay, the reason why we're doing this is it is a closed surface, but it's over this surface here. It's not over a surface like that. And so that's actually really confusing because basically that is the terminology that actually you'll see in textbooks. So you'll see the same terminology here. Sometimes this is zero, and that's going to be a surface like that, like a balloon, okay? This one here refers to basically we're integrating over this loop, over the area of that hole there. And that is very confusing, but that's actually the terminology that's really used in textbooks and how physicists do it. So that's actually really confusing. And then as far as this one here, I said if I move the magnet up and down, what would happen? That's right. This current's going to change direction. So it's going to be going like this, and then it's going to be going like this, and then like this, and like that. It's going to be changing directions. Hey, what is that called? Yes, alternating current. That's actually how you make alternating current. So most of us get, in this part, we get either our power from NISEG or from RG&E. So how does RG&E make AC current? Well, basically they have a whole bunch of rings like this, and then they basically have a whole bunch of bar magnets, and they have a whole room full of monkeys. So here's a monkey, and they have all the monkeys in unison move their magnets up and down like this. And that's actually how we produce AC current in this country, with monkeys and these loops and bar magnets. Some of the things I'm saying are even true. Okay, well, I'll show you actually how you can do this in a more sophisticated fashion. We'll work out the mathematics of this. But what we can see is that even by this simple example here, this is ultimately how we're going to get AC current by a variation in this. The variation is going to be we're going to have a loop, and we're going to rotate this loop in a magnetic field. And you'll have some sort of turbine to basically spin your loop. And you either use waterfalls, or you use coal plants, or you use nuclear power plants, or you use something, but some way that loop is getting spun in a magnetic field, and that's going to produce our AC power. Okay, so let's do more examples. That's all we're going to do today. Actually, let's do this in red. So here's another example. Okay, so this is some sort of external field. What I'm going to do is I'm going to take a loop here, and I'm going to move this loop into the magnetic field. And I want to ask, we're going to do a couple things. We're going to say, what's going to be the induced current? And we're going to say, oh, one other thing. This B is a constant. B is a constant. So we're going to ask a couple things. We're going to say, we're going to take this loop, we're going to move it in here. What's going to be the induced current as this loop gets inside the field, when it's entirely inside the field, and when it gets outside of the field? So what we want to do is, for part A, we want to find the induced current. And by that, I mean only the direction. We'll worry about the magnitude in a little bit. So find the induced current as the loop enters the field. So right when it's going inside here like that, what is it going to be? For B, find the induced current once the loop is entirely inside the field. Okay, And for the last part, we want to find out as that loop exits the field, what's the induced current. So find the induced current as the loop exits the field. Okay, so they're the three things we're going to have, and this is going to illustrate a lot of really nice things. Okay, so let's do part A. So I'm going to draw this loop partly inside the loop, partly inside the field and partly outside. So this is going to be part A. And again, remember, we're moving that loop this way. Okay, so what is the magnetic flux doing as we move this inside here? Is it increasing or decreasing, and why? So I have the loop here, I'm pulling it inside here. As it enters, what's happening to the magnetic flux in there? Increasing, decreasing, what's it doing? Staying the same? I'm hearing an increasing. Confirmation. Increasing, yes, okay. So let's do that. So again, what we do here is that if you calculate the flux here, and again, I'm going to use that confusing notation, and it is confusing. So in this case here, what's going to happen? Well, that B is going in and the dA is going in, and I would work this out. Now the B is constant here, but why is this flux increasing? So the flux into the page through the loop increases as the loop enters the field. Okay, why is the flux increasing when the magnetic field is a constant? Somebody actually already, I saw that that was actually already answered by Everett, who, if I had read the entire, I just saw the increasing and stopped reading. Yeah, so he's already answered it. So as you move this inside here, what happens? More and more of this area here, right? Right now, this is the only area here, right? Only that area is contributing to the flux. But as this moves further and further inside here, I get more and more area in there, so I have more flux going through there. So what's going to happen is that that's actually increasing. So the magnetic flux going into this page is actually increasing in as that moves in. So what is this little loop going to do? You tell me, according to Lenz's law. Okay, so there's either no answer coming or it's taking too long for people to type. It's a fairly long thing to type. Okay, this has to oppose that change. And what is it? Okay, it was just too long to type. Okay, so increasing as more enters the loop, opposite the increase B field and creates a current. Yes. So as this moves in, you have more flux going into the board, increasing the flux into the page. So this thing to oppose it has to create its own magnetic field coming out of the page. So go like this. Okay, so that's the B field. This is the induced B field. B field of the loop. And it has to be in that direction to oppose the increase. So this is an increased flux going into the board to oppose that change, as it has to create its own B field coming out of the board to oppose that change. So how do you have to have a current there? Well, to get that current, you have to have the induced current going this way. So this right here is the direction of the induced current. That's your induced current. Now, so if I have this, so this is the direction of the induced current, what would be the force on this loop? So if I had this loop and if I'm pulling it inside here, when I get inside here, I'm going to actually really feel a drag. I mean, it's going to come inside. I'm going to have to physically pull that. I'm going to feel that on my hand, and you can feel it actually quite a bit. It's shocking just how strong that force is. Why? Here I have a wire in a magnetic field. How do I find the force on a magnetic field? Recall, The force on a current carrying wire in a magnetic field is IL cross B. Let's do that. So I have four sections of the wire, here, 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 and here. Okay, what would be the force on this outer part here? Well, there's a current, I, but there's no magnetic field outside here. So the force on this side here on that right end is 0. Now, what would be the force on this top part here? Well, eventually there's some current here in the field. And again, this B is your extra, when we do this, this is your external field. So that's your induced field. So that's your external. So it'd have L cross B. There'd be a force on that side like that. That would be the force on the bottom, on the top. Now let's do the bottom part here. How would that go? Well, now I have the current going to the right. The B field's still going in. So it's going to be IL cross B. That's going to be this force like that. Those two forces are going to cancel each other. But now what's going to happen over here? So what's going to happen over on this side here is that if I do the force here, if I do the, it's hard to deal with, okay, if I do the L, because the current's going that way, so the L crossing the B, that's going to be a force going this way. So when I actually grab hold of this wire and put it in here, I'm going to feel a force on my hand, which is quite large on this loop, going like that, and that's actually opposing this. That's the opposing part. Okay, does that make sense? Okay, now let's do the part where it's entirely inside here. So this is part B. So let's say now this is entirely inside here and I'm moving it like this. So here's my V. The question is, what is the induced current here? So once this is entirely inside here and if I'm moving this along, what is the direction of my induced current? Now pause and wait for an answer. And also tell me why. Induced current should be 0, that's right. Because what does Lenz's law state? I mean, is connected with Faraday's law. Remember, it's this minus the time rate of change of the magnetic flux. Okay, if you're inside here, if you're entirely inside here, what's happening to the magnetic flux? Well, if you're entirely inside here, remember the B field is constant. The flux through here is constant. The flux equals a constant. What's the time rate of change of a constant? That's 0. There is no induced EMF. If there's no induced EMF, there's going to be absolutely no current. So in this case here, the I induced equals 0. That's pretty cool. So first of all, I have this counterclockwise current, and then once it's entirely inside here, that current goes to 0. Now the question is, what happens when we get outside here? So now I'm going to repeat this picture. But now let's do it for the case of pulling outside here. And after we do this, I'm going to explain how an EM pulse works and why Canada basically blew their power grid. I think it was in the late 90s, maybe mid 90s. You can Google this and find out, and they'll tell you the details of it. It's actually quite cool. Okay, so we're going to exit the field. So here's our loop, and now we're coming out. Okay, so we always have to ask ourselves, what is the change in flux? Well, the change in flux is going to be decreasing. So as the loop exits the field, the magnetic flux, I'll just say flux, into the loop decreases. And how am I doing with time? Okay, the magnetic flux into the loop decreases. So what does this loop have to do? This loop here has to create its own magnetic field going in the same direction to bring that flux back up to what it was. So the flux going in is getting weaker. How can this prevent that change? Again, you're always opposing the change. At the changes it's getting weaker in this direction, it has to create its own B field going in the same direction. Right, so this is going to create its own B field going in the same direction here. So this is the induced B field opposing the decreasing flux. So how does that current have to go? Well, I take my right hand, I point my finger in the direction of that induced current, my finger is wrapped like this. That has to be the direction of the induced field, of the induced current. Now I can ask, what's going to be the force that I'm going to experience as I pull that outside here? Well, again, I'm going to apply F equals I L cross B to each of these four sides. So if I'm on this left side, there's no B field here. There's a current, right? This is my I induced. I have an I induced, but I have no B field. So there's going to be no force on this side. But like up here on the top, this part here where it's in the current, it's in the field, I mean, I do, remember L is always in the direction of I. So it's L crossed into B, that force is up like this. And again, remember that B, this is your external field. It's that red. It's not gonna be the blue, it's gonna be the red. If you do down here, it's L crossed into B, that force is like that. These two forces cancel. But now if we look down here, the L's going, the I's going this way, so the L's going that way. So it's L cross B, that's gonna be the force going this way. So if I grab this and physically try to move this like this, I'm actually gonna feel that on my hand. I'm gonna feel this a lot on my hand. So what I wanna do is I'm going to, okay, so with that said, is there any questions? Okay, so I want to explain what, how an EM pulse weapon works. I'm going to do this basically by talking about what happens if you have the sun and solar flares. So let's actually go through and I'm going to draw a picture of how the power grid looks. So here's our little house. This right here, this will be basically, let's say this is RG&E or NICEG. Or whatever power, wherever your family gets power from, that's what it is. Now, how does this work? Well, they produce power. They basically have wires going into your house here like this. Here's your little light bulb. That's a little light bulb symbol, and this goes back here like that. Okay. And what do? They send current this way, and it comes out, it comes in here like that, and that lights up your house. That's how the power grid works. Yes, I know it's more complicated than that, but this is going to work. Now, is there any magnetic fields here? Well, there is a magnetic field, and there's a magnetic field from the Earth, right? So if I were to draw the magnetic field from the Earth, it would be something like this. So this is the magnetic field from the Earth. And that doesn't change, it's pretty much stable like that, and so life is all good and happy, and we don't have any problem. Okay, now what happens if you have a massive solar flare hit the Earth? Well, this is pretty cool. And if you can actually get on some websites and they'll have actually computer simulations showing how this goes. It turns out this is actually a highly active area of research if you do kind of plasma physics or some space physics. The physics of it is absolutely pathological. Let's say here's the sun, okay? And let's say here's the Earth. Now the Earth has a magnetic field. Remember, the Earth is tilted like this on its axis and it has a magnetic field like this. That's the magnetic field of the Earth. Now, let's say we have some solar flare coming out like this. So we have some massive ejection coming from the sun. And these are all charged particles. It's basically protons is what it is effectively, and some electrons as well. But let's say this is really, really massive. When this hits the field here like this, if you look at the interaction between basically the solar flare and this magnetic field, the magnetic field of the Earth actually physically changes. When this hits here, it actually bends like this. Actually, it's quite dramatic. Again, I can try to find the websites and I can show you the computer, you can look at the computer simulation yourself. But when this actually hits, if this is strong enough, this physically changes how this looks. So let's go back over here. So if this massive solar flare hits the Earth's magnetic field, and if this changes, what happens? Well, maybe the magnetic field now changes. Maybe now it's going like this. I have no idea how it's going. I'm just drawing a random thing like this. It's changing. Now what's happening? Well, that's changing the flux through that loop. So the solar flare comes out, hits the magnetic field of the Earth. This physically changes direction. Again, remember our flux is this integral of B dot dA. Okay, you're changing the angle. First of all, you're changing the strength of the magnetic field, but you're also changing the angle that the magnetic field makes with this loop area here. So you're changing the flux here. Well, what happens if you change the flux through this loop here? Well, by Lenz's law, this loop is going to actually induce another current. So what's going to happen is when that magnetic field changes through here, this actually induces a current going in the opposite direction to oppose that change. And that current in this case here can actually be quite strong. And so you basically have this you have this induced current going in the opposite direction, which was not anticipated at all in these circuits, and it completely blew out the Canadian power grid and on the East Coast. And it was, I think, out for several days. It was actually a massive disruption. It affected millions of people. It was quite incredible. But that's all it is Lenz's law. This is the basis for an electromagnetic pulse weapon. So if you have an electromagnetic pulse weapon, what you do is you basically have a pulse, and it turns out we're going to see later on you can actually do this with an electric field as well. But let's say you had some sort of weapon that actually had a really strongly changing magnetic field. So maybe you have some missile here like this. This is your missile, and there's some electronics in here. If you had a weapon which actually had some sort of magnetic field here changing rapidly with time, what would happen then? That's going to induce a whole bunch of induced currents in your circuit board. And those induced current in the circuit boards, if it's not basically designed to handle that, is going to completely wipe out the electronics in your circuit board. And that's the whole basis for an electromagnetic pulse weapon, is this basically Faraday's law. You basically have a rapidly changing magnetic field that's going to then induce some a current that's going to occur in your circuit board, and that's going to wipe out your electronics. And that's the whole basis for how those weapons work. So if you happen to watch the GoldenEye, which is one of the early James Bond films with Pierce Brosnan, it's the first one here is James Bond. That was the whole basis for the GoldenEye weapon, that it was an electromagnetic pulse weapon. Are there questions with that? And if not, we will start with demonstrations on Monday, because class is actually over. So I'll have office hours today from 1 to 2:30. Have a great weekend. If you happen to celebrate Easter, have a great Easter. If not, have a great day anyways. And I will see you Monday. Oh, somebody wants to know when is our next test? In the future, when I decide when one is going to be. I have not decided that yet. Sorry.